Going live with the gradual quanta. So we are broadcasting on Zoom and on Periscope. So let me show you the address for both Zoom going and live with the gradual quanta. So we are broadcasting on Zoom and on okay, let's see. So the web page here. So there is a QR code for Zoom here and a QR code for Periscope. So with Zoom, you can participate verbally and maybe a little bit with video and a little window on the side. And with Periscope, you just read only, so you just attend the meeting, but without participating, except with the chat. I mean, you can text, no problem. So today, what we will do is we want to do some coding. We are developing the Mychelium blockchain. And so basically, we developed the interface for adding blocks, merging blocks, and all those things. And today we will address the merging blocks, which is a little bit tricky. So we will see if we can code indirect that function. So basically, let's see what's the problem is that every file, every document that you add to a blockchain is considered as a block. And a block is any type of data. Can be a Word document, can be an Excel sheet, can be an image, can be just a text, can be a transaction, anything. And with that document, we compute a hash, meaning a code that is securing the document. That means that if you have the code, you can access the document. If you change the code, the document is not accessible anymore. And if you change the document, then the code is not valid. So it's a way of guaranteeing the integrity of this document. And so, for instance, let me do it for an example. Let's do a text. There is my first block here. So, so it's just a text file here. It's in the format of Markdown, but it can be anything. And so it's just a text, and the block chain will be a document that is linked to a previous document, previous version. So that's what we do is that we have a field that we call it previous. We can call it, anyway, but as long as we do a reference to the previous document, then it is a blockchain. So that's how a blockchain is. It's just a document cryptographically referencing another document, basically, and you have a chain of documents. So if we do, for instance, let's see if I can do a little blockchain. Try to do it visually. So that means for a blockchain, we have to start with one initial document. Do I have a file that is called blocked.dot? So dot is a way of doing graphical little graphs representation. Here you go. So it's blockchain can be a directed acyclic graph, meaning that every document can point to a previous document or to more than one previous document if you want, because a document can have two parents, that type of thing, meaning it belongs to two blockchains. Okay, so we have to start with one first block that will be the genesis block. And so if I do compile this graph, there will be one block. So let's see, dot, here you go, and it's here. So one block, which is just the genesis. Can we zoom in on that one? I don't know. Yeah, maybe here. Yes, here you go. Genesis. And if we want extra block, let's say we have documents. And so you have to have genesis, the new block, and documents one that will point to Genesis, for instance, which is the previous block because it's the first one. And Genesis does not point to anything, at least in blockchain. In our way of doing blockchain, we do loop them back. So we call it block rings instead of blockchains. And that means it point to the head of the chain. And so if I do something like that, for instance, and we have the graphical representation of what just I did. And so how do you do zoom back, zoom 100%? Oh, I made a mistake. Genesis can point back to head. We can also put the head as a square shape. No, circle. Why did I do square shape for the head? Head. Box. There you go. So you got doc1 that point to Genesis, and that point to head if we want to loop it back, and so that means the head also point to the new one. So I have to correct that. The head point to doc1. That's what is important. So we can say head, or we put that on top. Head point to doc1 and the point to head again. And we can probably style this as dotted line. Let's see how it works. There you go. So head, doc, and then Genesis back to head. Okay, so that's blockchain with one document. You notice that the head is a special type of document that has a pointer to the head of the blockchain, and that means, oh, this one does need not to be dotted line because it's the real blockchain. This one is a return thing. Let's see. So let's do it again. I think I have it here. Blocks. And so dotted lines, that means we have to separate the lines. Genesis. Here you go. So to one block, so the head pointed to doc1, which is the first block, and the, well, two block, because if you count the Genesis as a block, then it's two block. There you go, like that, perfect. So now if we want to add one more block in our blockchain, what does that mean? Is that we will do just add another block. That's simply that referred to the previous one. So that the new block will be doc2, and then the doc2 needs to link to doc1. And then that means you have the following chain, doc2 and so on. So, and a hash. So a hash is the summary of the block. Like I said, it's a secure way of pointing to a block, and we do that by the command IPMS, so Interplanetary Mutable System. That's the system behind the Mychelium blockchain, and we can say IPMS add, and let's say I add the image that I just generated about the blockchain. And so, and give me a QM code that starts with the letter QM. And so that's the hash. And that means with that function, if I do X, I open my web browser with the local address that will be localhost, for instance, localhost at the port 8080. No, I don't know if it's 8080. I think it's something else. Let me check where it is. My IPMS server is running at 8197. And so you can specify the hash value, and then you have the proper file. And so if you see in the address bar, you have the code here. If I change another, just one letter, boom, then it does not find. It's waiting to find it, but it doesn't find the. It will error out when it says there is no document attached to that. And if I do change, make a slight change, for instance, adding a doc3. So if I add a doc3 in my blockchain, for instance, doc3 in the chain, I can write everything on the one line, and I will have the chain that will be like this, doc3, and if I compute the hash of that one, you see it's not the same. It used to end with FBD and now it's end with F38. So I mean the code is the same, it's different. And so that means to have the new version, so if I try to get the same old version with the FBD, copy, let's paste the hash there, and so that's always the same of the previous one. So it's a permanent address. At any time that I refer with that hash, I have the same old pictures. And if I get the new one, here you go, you have the new one here. And so there is probably a better way of seeing that with the web interface, which is 121 perhaps? No. 20? Oh, where it is. 5121, yes. Web UI. And you can look for the hash, copy, paste, explore. So that's the explorer. And so give me the hash, give me the size. It didn't say that it's an image because it doesn't know what it is. But let's see if I can do it differently. Well, we can view on the gateway. So on the gateway, what does that mean? Is that it's on any server that is running the IPFS network, within an IPFS network, has access to that particular image by just knowing the key. So the hash is a way of accessing this anywhere on the planet. So I can access it on a gateway, don't open to the public. I can access it from any countries, even behind a firewall, like behind the Chinese wall. You still have access to that because everything is local in a peer-to-peer network. Okay, so that's the blockchain. And so the thing is that the particularities of the blockchain that we use is that we don't have a global replica of every of the blockchain, the approved blockchain in every node of the network. So we don't want to waste resources. So in that sense, everybody has the portion of the blockchain, the portion that's matter to them. So it's like a personal view of the blockchain, and it can be just a fractional part of the overall blockchain. And so we need to have a function to merge them when we want to consolidate the data. For instance, if I do transaction with person B, and person A, and so the blockchain, I have the blockchain A, I have the blockchain B. If I do a transaction, I need to consolidate those two views, and that's the merge function. And so basically it's like merging two documents. Like if I have a document 3 and a document 3B, then how do I make a document 4 with the 3 and the 3B, and then add it to the blockchain, or update the previous document if it's required. So that means we have like a chain of different versions. So document v1. Can I do a dash? I don't know. Let's see. O underscore v1. Well, if it's a chain, it's the highest version that is first because we chain with the previous version. Doc v2, doc v1, doc v0, and so that's one version that will be the head of your blockchain, for instance. And so let's see, I put that in a file image that I call DAG for directed acyclic graph. DAG, and I I made a mistake probably somewhere. Yeah, the head needs to not be in square brackets. It's because I wanted to have the head square. No, shape box. Let's put the genesis too. Genesis circle, for instance. Okay. Tag. So here you go. Oh, I didn't link the genesis, but anyway. So we can link to the genesis block. And so any document that is linked is a blockchain. Here you go. So that's my blockchain. And imagine that I have another version. So this one is a Michel version. And you have yours. That is a different one. That would be, so you have another version 2, version 1, you have a version 2b, and then you have a version, even a version 4. Oops. For instance, let's see if the graph is interesting enough for us. So, well, there is no head. And even you prepare v5, for instance, also. So you have yours blockchain, you have mine. I mean, I didn't do any updates, or maybe I do an update. Let's do it an v4b, so that at least we have a chain. So I have this blockchain here. And you have yours there. There's 2.0, but that's fine. And so what we want to do is we want to merge v5 with v4. And so how we do that? Actually, that might be v5b if we call it the one in the other branch. And so we don't need to double the rows from this one. So you have the two chains, and now we want to say, hey, how do we agree on those chains, and then how do we merge them? And so those two. And so we have to find out the difference that we have applied since a common node. So if we see the V3, the V3 is common, and then we want to apply the change from V3 to V4B, and from V3 to V4, and from V4B to V5B. And so hopefully there will be no conflict during those applying those changes. If there is conflict, then we flag out, and then we have to negotiate which are the changes that we want to keep, which one we want to modify. So the problem that we have for the merge is that we have to find the closest common ancestors. And so for the ancestors from 5 and 4, 5B and 4 is the dog3. The ancestors, for instance, of dog V2 and V5B will be V2 because they are on the same chain. So that's the question that we want to, the problem we want to resolve. So that means we want to write a little program that is called bin closest common ancestors, and we have to sort out the thing. Let me write down a little bit differently the graph, because so that I can read all the edges of the graph in an easier way. So that means I use only one row per line, so that it will be easier to parse. Doc V3, doc V2B, doc V1B. So what that's for your blockchain, and for mine that will be for mine. Okay, and so let's verify that the graph is not broken. Oops, where's this one? Yeah, that sounds good. We can put the head and yours also, because if you there you go. And so V5 and V4, we want to make the difference between yours and mine. And so in that case, with this little graph, the graph here, we will generate a list of the edges. And so I have a dot to YAML. I wrote a little program that is dot YAML. I don't know why it is. It's not beam, it's bin. Dot to YAML. And we pass the dot file as an argument. And it generates the list of all the edges. So doc V0 goes to Genesis, doc V1 goes to V1. So it's all the parents listed. And so then I can load the graph in the program. So load that graph. So I probably need to do a function, use a YAML parser. use YAML CQM load file. I probably will have to do the dump function so that I will be able to check. So in that case, we wrote sub load. So what I'm using here, I'm using Perl for doing the experiment because I'm relatively fluent at Perl, and so. But you can use any type of language that I mean scripting language or even more advanced language. The advantage of the scripting language like Perl is that we can do experiment quickly. So load DAG. That will receive as input a file. A YAML file. And I will just output the DAG itself, the graph itself. And so return load file $YAML file. And that will be okay, just that. I mean, that's pretty straightforward. We don't need well, I mean, just in case we do other processing after, you can keep it in a subroutine, but I mean, it's probably pointless right now to have that subroutine that just do load, nothing else. And so we put the file, and the file is, what is the name, dag.YAML. Okay, and I will do a print to check DAG, and that will be the graph that I just loaded. Well, I did hard-coded the things. Maybe the file will put it as an argument. My $files chiefs $files. And this one has been cc dag model. Oh, syntax error. I don't know how to write Perl in one shot. Yeah, you need a comma somewhere. Okay. Oh, I don't have it. I don't have the YAML module. So let's see if I do source config. Do I have the YAML there? No. Echo perl 5lib $perl5lib. Why I don't have the YAML? Did I make a typo? No. Well, let's try to up here. No. Bootstrap perl5. I didn't. I thought I did the YAML. Yeah, it's here. Well, let's try to reinstall it. It's up to date. So something is not right. Oh, it's a capital S. That's why. Donc, let's do again the program. Here you go. I got a hash that is returned. So if I want to graph load file, graph, if I need to do dump of the hash, that would be more visible, at least more explicit. Here you go. So you have all the trees with all the linked. And so now that I have the link, I need to find the common ancestors. So let's do a command, a routine, CCA, capital CCA, list closest common ancestors, closest common ancestors. So how we would do that? Well, we can look at our graph here. Maybe make it bigger, not smaller, bigger. And so what we want to do, can we do, yeah. We want to find this node. So how the brain is processing that, and because the thing is that if the chain is super long, we don't want to process all the nodes. Imagine you have 10,000 nodes here, you don't want to load it all. And so how we do that, probably we do like our brain is doing it. And so what we do is that we start from both heads. So there is head 1 and head 2. Actually, it's not yours, it's pointing on V5, right? And mine on V4. S1, L1, L2. And so here you go, so head 1 and N2. And so we start from the head, and then we just like notice all the ancestors. So all the ancestors of those ones is this type of graph here. So for instance, we can put a color on all the ancestors of mine. And so what does that mean is that we'll have doc v4, doc v3. No, v4 we cannot count as ancestors, but let's say 3 is ancestors, 2 is ancestors. Meaning every node on that side of the list is ancestors, right? Doc v1, doc v0, and doc v. I do have Genesis then. Genesis. So all those are ancestors of doc v4. And so we will place a color like we do red, all those ancestors, so that we mark them. So all those are the ancestors of v4. And so what I want to do is I find the ancestors of v5b, and we see the one that are. Let's see if I put the ancestors of v5b blue, the one that will be purple will be the ancestors of so 5b. I put blue, so that will be ancestor of 5b will be 4b. We have 4b, ancestor of 4b is v3. Ancestor of v3 is, oh, I forgot. Yeah, this one is also ancestors. It was supposed to be red, because there's 2 links. Well, yeah, I mean, it has to produce 2 parents. So I mean, it's possible in a blockchain. It's kind of a little bit tricky to have 2 parents, but I mean, we can. I mean, the default interface does not allow double link, but if it's possible, then someone will do it. Is there a 1B? Yeah, there is a 1B. So 1B also are ancestors of v4. And so v3 is ancestors, and then all the other ones are also ancestors. So v3, v2b, doc v2b, doc v1b, doc v1. Yes, probably doc v2 is v2 and ancestors. Let's see the graph. Where's my graph? That's the whole graph. This one. Did I name? Yeah, I want to blue this one. No, v1 is not ancestors of. Well, yeah, if the doc3 is a common one, it is. It's a v2 too. So that's what we have, and so we have to remember the one that were red because it doesn't do purple. And so how we do? Yeah, with the graph we don't know exactly how to do it. We probably have to. Well, they're all purple except v4. Because if you look at the red, let's look at the red, and then we transform all the red in purple. Okay, so these ones are the ancestors of dv4, and so color blue, and then if we do that, we have the mix. Here you go. So those were the red, but now they are blue because they are ancestors of v5. Okay, so that's what it is. And then now we want to have the closest one. So to have the closest one, there is a way of doing it. Is that for every parent of the purple one, we will do have a counter that counts. We'll do +1. Let's see. Do I have a +1? Oh, I didn't save it. Yeah, +1. No, not on V. Not on V4. Doc V3. Does it work on the arc? Let's see. No, that says the content. Oh. Donc, let's do it differently. The arc v3 to v2, we do +1. This one we do label +1. Label. So all the purple nodes, we add +1 to a little counter type of thing. To the we add +1 to the parents of those things. So let's see, +1, +1, +1, yes, and then we have to do +1 on the other side too. So v2b here. Label +1. Label +1. I'm missing one. V3. This one. So now if we sum up all the values that arrive with +1, what does that mean? Is that with the Genesis block, we have only one. So label counts equals 1. Oh wow. I have to put repeat the name Genesis here. Genesis. How did I rotate it? There you go, Genesis count 1. So on doc v0 there's 2 coming in, so v0 will be doc v0. Let me put a section that is counter value counts value. Okay, so the Genesis value is 1. Doc v0 value is 2. Doc v1 v1 value is 1. v1b value is 1, 2. v2 and v2b is 1, 2. v3 doesn't have purple parents, so value will be 0 because there is no parent. There you go. So what we have, v3, doc v3, label v3b is not v3b, is v3 anyway. And okay, so 0, 1, oh, doc v2, I didn't have the v2 because I made a typo. There you go. So v2 is 1, v1 is 1, v0 is 2, v1b is 1, v2b is 1, Genesis is 1. So in the purple node set, the one that has the smallest count is the closest ancestors. So the one that has the counts to 0 is the closest ancestors. So closest ancestors of 5b and 4 is b3. And so let's deploy this type of algorithm on my program now. So where do I have the program? Here it is. So we have 3 paths, apparently, is list ancestors of the first graph. Let's put graph A, graph B. This is of graph, no, graph of a node. And that's the head node. Graph A. Ancestors of A equals get ancestors of A. Then ancestors of B get ancestors of B. Okay, now we do have mark A equals, we will mark A with color. Colors equals, well, not equals, but blue. How do we do that? We can increment the value, because then if it's 0, that's not been colored. If it's 1, it's colored, and if it's 2, will be the purple one, right? Or the blue. 1 is red, blue is 2, and I mean if we add, there will be 3 would be purple. Okay, then we do, oh, we have to have only one graph. Yeah, it's the whole graph. Well, I need to pass the graph. So I mark in the graph the AA. Then in the graph I mark all the AB cells with color 2. Then all the purple, so the common ancestors get node which color equals 3, right? Where within the graph where color equals 3, colors 3. And then for each node in keys in the graph CA, node slash previous, then we have to color. So all the purple need to add 1 to the path. Blue node, no, that was red. The first one is red. Red nodes. This one is blue nodes. That will be the perl nodes. Now for 2, previous, so previous count plus 1 plus second one. And then the closest common ancestor is get node in a graph where counts equals 0. Return CA. There you go. So we have a first attempt to the function that find the closest ancestors, and so that means we have to write a few sub functions like get ancestors, and we want to also the mark function. And I think there was another one somewhere, get node. And we'll be okay with that. So that's the way of doing the common ancestor. Then we can apply the change one by one. So that's it for today. We can probably stop